Welcome back to Low to High Level. You've probably seen that I've been in the same clothes because I'm recording all these intros on the same day. So, last time we went and saw that we could create from those 1-bit systems, 4-bit systems. Well, today we're going to up the ante yet again. We're going to take those 4-bit systems and migrate them to 8 bits. With 8 bits, we can make a pretty simple processor that can do a lot of things. So, we're going to use those 8-bit systems, and we're going to upgrade them as we go. Our plan is to allow us to enable and disable these systems as we choose. And if we can do that, we can create an ALU, or an Arithmetic Logic Unit. That is our goal for this episode. So, I'm not going to keep you waiting. Let's go see it. Alright, so this system is going to be a little easier. Since we have the 4-bit systems, we just need to put 2 of them together to create an 8-bit. So, we're going to take our 8 inputs for each side, and we'll have 8 outputs for what we're going to make. There we go. And now we're going to put 2 ands together. So each part goes right into the first, and the other parts go into the end. So the first go into the first, the ends go into the ends. And that would create our 8-bit and. Our 8-bit ORs are very much the same. We're creating our 8 inputs and 8 outputs, and putting 2 ORs together, tops go into the tops, bottoms go into the bottoms. Simple as that, just get it together and we create our ORs. When we make our XORs, we essentially do the same thing. We put the tops to the tops, bottoms to the bottoms, and we have XORs. It's really that simple. We just keep doing the same thing. And finally, we create our 8-bit knots. We have 8 inputs, 8 outputs. Simple as that. Just put it together and you have knots. This leads to the big one, the 8-bit adder. We have to have a carry in as well as a carry out, but we have our 8 inputs in each side and we ripple them together, creating our 8-bit adder. We put the tops to the tops, bottoms to the bottoms, and there we go, 8-bit adder. Earlier when I was recording this video, I noticed that I lost some data. It's frustrating when this happens, and unfortunately I couldn't do anything. OBS glitched out. However, I can try to explain what happened. After I created my 8-bit adder, we moved on to the more important parts of the ALU. We created a enable circuit, which is essentially a enable with that ands a bunch of stuff together to say, hey, is this enabled? Then do this. And I also took our adder and allowed you to subtract with it as well. I'm going to try to explain it as best as I can in the next segment. If it doesn't work out, let me know in the comments and I can do a more in-depth of how this works. As I lost some data, here's me trying to give a brief explanation. I created an adding and subtracting system, so if you press the subtract button, it will allow you to go into subtract mode, and the second argument will be subtracted from the first. The way it does it is by using a little system called 2's complement. And to do that, you invert the data that you're doing and add 1. And by adding 1, we can do that. With that, we can do other things. So here's me showing that, hey, 0 minus 1 is -1, and there's a little carry because it thinks it's a big number. Other things can happen with this, and that will help us in the future. I also created a different system. I call it a selector. This means that I have 3 bits of input, and through that I can get a single output. And these outputs will determine what I will do with my computer. Say I add, I subtract, I AND, I OR, I XOR. All of these systems that I will need can be selected individually through this. This means that I can use less lines to get a single output when I'm creating my full system. Using this system, I also have an enabler. This says just one big AND gate, and all of the inputs are for one bit, and everything else is the other bits. So if it's enabled, it can do things. And for each system, I created an enabled version. So if I want to AND something, I have my inputs, but they will only output if the enabler is enabled. So in the future, I can do things with that. For example, I have an OR enabler. So if I want to OR things, I can enable my output. I also created an enabler for the adder and subtractor. This one does have a few extra things. I'm making sure that I can enable things, but I have an extra AND with the enable bit that says that for my output, just to make sure that things work. My subtract mode also is considered an enable, because if I'm enabling to add. If I'm subtracting, I'm also enabling to subtract. So in that case, I assumed that it will always be the same. That should make it a little more simple in the future to implement. At this point, I created a few more chips. This one is going to do 3 of our systems in one chip. It's going to do our adding, our subtracting, and our AND operator. And in order to get this to work, I have all of our outputs going to an OR. So this means that if one input is out, it'll just merge them all together to get it functioning. This also allows us to merge a few chips to make it easier to create a functional GPU. I have my adding, subtracting, and ANDing here, but there's a couple more chips that need to be put in place. That leads to my OR. So I'm doing OR, XOR, and NOT initially, and then I decided, you know what? I'm going to put NOT separately because it'll be more useful in another location. So here I'm taking my 8-bit enabled OR and my 8-bit enabled XOR, and if one of them is enabled, we do something with it. It's as simple as that. We're just putting these together to create these big chips that will eventually go into our ALU. There were a few systems that I wasn't so happy with. I have a bunch of stuff here, but I want to add a couple more features. This takes 8 inputs and 8 outputs, and it rotates them. So this is a rotate left, and there's also a rotate right. It takes the least significant bit, puts it at the top, and moves them all over 1. That's pretty much how it works. So here I'm creating an enabled version of rotate left, and I'll do the same for rotate right. From there, we can put it in another one of those chips. Remember when I got rid of the NOT earlier? Well, it's coming back to bite me. Here I'm going to create a NOT version that allows you to merge them. Since they all have 8 inputs and 8 outputs, we can use that. Here in real time, I'm going back to my selector. It takes a second. I have a little ALU that we've been working on, and here's our selector. We have a couple open bits from these 3 bits that we've enabled. So with those, we can do a few things. So what I'm going to do is add a couple more solutions to these. I'm going to have a rotate right and a rotate left output. This will be a little easier for us in the future. So here I'm creating those pins, and I'm looking at these. I have those single gates that we've used earlier, and I need to add them back to my library. This is just going here and starring them. It takes a couple seconds, but for the sake of keeping things simple, I've been keeping things simple, so I'm not overstimulating my mind. So, we're going to take a couple gates. We're going to say, if those two gates are enabled, but that last one is not, and we put those two together, then we will assume that that output is correct. We're having a little bit of bit issues because I may have accidentally added another bit, but we're fine. There we go. So that is selected. And finally, we have that last case of all of these. So if all of them are selected, then we are good. So if that's selected, and that's selected, then we have our final output. Perfect. That is just what needed. So our selector is updated. So now going back to our ALU that we've been working on, here is all the crazy stuff we've been up to. We have our enabled not, which we don't need anymore, because now we have a new case for the knots. It's in the rotate left, rotate right not system. We're going to put our not back, and we're going to take our rotate left and rotate right outputs and put them in there. And for our first significant bit, we're just going to add that straight to the ALU. This is going to make it a lot easier for us in the future, as we don't need to worry about it. It's all in one chip, a lot less to edit in the future. So slowly it takes time. All this is being shown in real time, as opposed to the simplified way I've been doing it. So as you can see, every single thing has to be clicked, dragged, clicked, and it takes forever. But I think it does show that making a computer is not simple by any means. And here is our ALU. This is a functional ALU with everything we wanted to do. So here we're rotating, or at least trying to rotate. I noticed a little thing that looked off to me, and that does not seem 100% right. So I spent a minute going back, double checking that all my bits are right, and all my inputs are right, and I hoped it worked, but it's not always perfect. Seems okay, so we'll see how it goes. There we go, that's our ALU. So as you've seen, we now have an ALU, or an Arithmetic Logic Unit. This is an extremely important step into creating a computer, as it is the most important part of the CPU, or the Central Processing Unit. That is what we have been focused on, and that is our goal. We're going to create a functional CPU that can do a lot of things. But in order to do something with that CPU, we need some way to access data. So we're going to be focused on the most important part of it, a little bit of memory. Our memory is going to be a system called a register. A register is a series of bits that can do things. In our simulation of the Boolean logic, we're going to keep it very simple. But in the future, we're going to migrate to a different way of doing things, emulation. So it's going to get really fun really quick. But now that we have an ALU, let's get closer to that memory. If you enjoyed this video, be sure to subscribe. If you'd like to see some other stuff, I've got a whole playlist right here. Alright, I'll see you later.